So, how do we describe motion in physics? This seems like it would be very simple, and in many ways it is, but we're going to introduce some new terminology that makes you think a little bit differently about how you describe motion in things around you. And so, first, we need to look at what is motion. Motion is the change in position over time. As we look at this, we do have to consider a frame of reference. So the frame of reference is a coordinate system for assigning positions in time. This is going to be exactly what you think of when you think of the phrase frame of reference. Um, as you are sitting in a specific location, and you look around at what looks like it's moving, what looks like it's not moving, that's going to depend on you. If you're driving a vehicle, things will look like they're moving from your frame of reference, but they may not look as though they're moving from another frame of reference. And so, anytime we establish something in physics, we're going to go back to from what frame of reference are we coming from as we describe that motion. And then as we look at position, position is a location relative to that frame of reference that we have established. In physics, we have a branch of physics called mechanics. Now, mechanics deals specifically with the study of motion. And so, over the next few chapters, we are going to be dealing with all types of mechanics and the study of motion. And specific are two type branches of mechanics that we're going to look at. The first is kinematics, which is how objects move. So, how are these objects actually moving? And then dynamics is the branch of mechanics explaining what causes the objects to move. So let's look at just a mathematical representation of motion. We are familiar with linear or one-dimensional motion. You've been doing the number line for many years now. And on a number line, your reference point is that starting point or the origin. And then direction on a number line is typically left and right. So to the right, you have positive, to the left, you have negative. But when you are measuring something vertically, then your reference point again can be where you're starting from. And that may depend on whether you're on the top of a cliff or the bottom of a valley. Again, your reference point's very important to that. But for vertical motion, up is positive and down is typically negative. A couple things I do want to point out as we get into formulas here, these subscripts are going to be very, very important. And so you'll notice these three subscripts here have a subscript that is I. The subscript is that little small letter down there. I stands for the initial value. So when you see a formula that has maybe some variable representing some part of that formula and a little subscript with an I, they are talking about initial or starting value. And then when you see this F with a specific variable, that is the final value for that. So for example, this T could represent time, initial time, final time. Ordered pairs are often used then to describe two parts. So we could have an initial time and initial placement or location. And they're going to give you that by the variable and the subscript. So now terms that we're going to use in this first section are distance and displacement. So distance is the total number of units traveled overall. But displacement is the change in positions between two distinct points. So displacement is not necessarily going to be the same as the distance because you are then comparing two different locations when you say displacement, whereas distance, you're just talking about how far you traveled overall, whether it was back and forth, distance is not going to have a direction. And so when you think about distance in a number line, we would say something like absolute value because we're really just looking at how far we have gone, not necessarily a direction. But displacement is going to specifically want to know the starting the final placement subtracting the starting placement. So if we look at distance versus displacement here in this example, if we start here at x sub 1 and we move to this point over here, and then from that point we move back, you can see that when we went from 1 to 4 meters, that would be 3 that we traveled. And then we went from 4 back to 2. So we traveled another 2 meters. So overall, the distance that we traveled, we moved 3 meters and another 2 meters. So we moved 5 meters altogether. However, if we look at displacement, displacement literally just wants where I ended, subtracting where I began. And so if I look at where I ended, well, I ended at 2 meters, which is my final location. And I started out at 1 meter. So my displacement here is only 1 meter, even though if I were walking, I would have walked 5 meters altogether. And so distance is going to be how far you moved collectively. Displacement is just how far away am I from where I started. And displacement considers direction. So in this case, from where I started, I moved in the positive direction. And so that's why it would have been a positive 1 meter. So if I look at an example like swimming in this pool here is 50 meters. Well, if I start here in lane 1 and I swim 50 meters this way and 50 meters back, 50 meters this way, 50 meters back, I did a total of 200 meters swimming. I went back and forth 4 times. However, my displacement, if I am back where I started from, is technically 0 because I am no distance away from where I started, no displacement. And so, distance here, I've traveled 200 meters going back and forth. But displacement, I'm right back where I started from. So, my displacement here would be 0. Now, displacement can also be vertical. So in this particular graph, if they want to know my vertical displacement, well, that's going to be my starting point up to my ending point. And again, we are going to determine that even if it's vertical using our y final minus our initial. And keep in mind, it can be negative. So if I were to go up and all the way back down past it, I could potentially have a negative movement for displacement. So let's look at this example together. It says a family leaves its campsite and travels by car to a picnic area on the west side of the lake. A sign at the campsite says that the picnic area is 2 kilometers west by boat, but the children notice that the odometer advances by 10 kilometers during the trip, right? So what we're looking at here is driving. They left the campsite and they drove around all the way to the picnic area. So the distance traveled is going to be this 10 kilometers here. That's how far they traveled distance-wise. However, if I were to ask you about displacement, displacement is not 10 kilometers because where they ended compared to where they started is only going to be this 2 kilometers. So in this particular example, their distance would be 10 kilometers, their displacement would be 2 kilometers. And in this particular case, it says west. So when I'm looking at north, south, east, and west, north is positive, south is negative. East is positive, west is negative. So in this case, I have to be extremely specific. If I am going to say my displacement, I need to give a direction. And so I either need to say 2 kilometers west, or I need to say -2 kilometers, meaning that I went west that direction. I will say for the most part, when we use a north, south, east, west, we're typically going to actually use those directional notations there. But displacement requires a direction. So I must indicate not just the 2 kilometers, but also which direction I am from where I started. And the reason we do this is because of these next two terms. The term scalar is a quantity that only has what we call magnitude. The magnitude is going to be that numeric value, um, the 10 kilometers, right? 10 kilometers is a scalar. But a vector contains magnitude and direction. And so distance is going to be a scalar because direction doesn't matter with distance. But displacement is going to be a vector because with displacement, I have to say 2 kilometers west, and I have to give a direction, not just a numeric value. Some examples of scalars versus vectors. If I'm talking about speed, I'm going to say something like 50 miles an hour. But if I talk about velocity, then I'm going to say 50 miles per hour north or 50 miles per hour east. And I am going to give a direction for velocity. If I say mass, then I'm just going to give you the number of grams that this apple has. But weight indicates a direction. It doesn't seem like it would, but gravity is pulling that object down, which is causing you to see something on that scale. So when we have a weight, then the weight automatically indicates a direction. And so that's a vector. Some other examples of scalars are volume or time. These just require a number, not a direction. But something like friction requires a direction because I could have friction pushing down this particular ramp or pushing against the ramp or gravity pulling down on it as well. And so these are just some very few examples of scalar versus vector.